Pressure, flow, resistance. Need you to relax. Let it come to you. Let it come to, I'm going to walk you through step by step. Step by step. Let it come to you. Don't fight it. Don't fight it. We'll go through it. We'll go through it. Here we go. Just replace that with bicarb. Replace that with CO2. And you can do the whole thing with Henderson-Hasselbalch. If you don't want to do the equation, you don't have to use it. It's totally up to you. Use your learning style. Do what works for you. All I'm going to do is this chemical reaction. I can do everything acid-base-wise with this chemical reaction. You can also do it with the Henderson-Hasselbalch. Your choice, your style. Do whatever fits you. I'm going to use this. Okay? I'm going to use this. It's a very basic chemical reaction, and I just remember basic chemistry. Basic chemistry. All right. Who regulates CO2? The lungs. The lungs. Who regulates CO2? The lungs. It's inversely related to ventilation. All right, who regulates hydrogen and bicarb? The kidneys. The kidneys. There's your players right there. Lungs for CO2, kidneys for hydrogen and bicarb. All right, this is the story of the rabbit and the hare. The rabbit and the hare. The tortoise and the hare. Tortoise and the hare. The lungs. The lungs is the hare. All right, they're fast. Take them that long. Bam, bam. They move fast. They're not as good, but they're fast. Kidneys are the tortoise. Takes them a while, but they're very good at compensating. They're very good at compensating. All right, so this basic chemical reaction. This is what we're going to do. We just have silly fun. We go 1, 2, 3, 1, 2, 3. I'll show you how you do this. 1, 2, 3. 1, 2, 3. That's all you have to do. 3 questions. First question we're going to ask is, what is the osis? Meaning acidosis or alkalosis. pH is low, then you have an acidosis. pH is high, you have an alkalosis. That one's pretty straightforward. Does anybody have a problem with that question? You're okay with that one? Okay, good. Now, just to warn you, in real life, you could have a pH in the normal range and still have an acid-base disturbance. That's okay. We'll be able to figure it out. I'll show you. But we're going to start with that basic construct. All right, question number 2 will be, what is the cause of the osis? And what we're going to do is we're not going to follow the yellow brick road. We're going to follow the bicarbonate trail. We're going to follow the bicarbonate trail. And I'll show you how we do it. Third, and just be prepared. Third, be prepared. You have to make a calculation. You have to determine if compensation occurred. You must make a calculation. Okay? This is not integrals. You're not doing complex math. They're going to be basic mathematical formulas you have to remember. You have to remember. Okay? So that's what we're going to do. Question 1, question 2, question 3. We're always going to go in order. Now let me give you the basis of what's going on with questions 2 and 3. Okay? Questions 2 and 3. Before we do that, we have 4 basic acid-base disturbances. The first is a respiratory acidosis, too much CO2. Second is a metabolic acidosis. Means you have too much hydrogen or you lost bicarb. Base, bicarb is the base. 3, a respiratory alkalosis. That means you don't have enough CO2. And 4, a metabolic alkalosis. That means you lost hydrogen or you added base. So I only have 4 basic disturbances. We are going to follow the bicarbonate trail. Question number 2. Question number 2 will get us to this point. It will define the primary disturbance. So we're going to look at pH first, then we're going to look at bicarb. That will define the primary disturbance. Notice, I have 2 ways I can get an acidosis. Either the respiratory system, holding on to CO2, or it's not respiratory. We lump everything not respiratory into metabolic. Doesn't mean metabolism changed, we just call it metabolic. We have 2 forms of alkalosis. Either the lungs cause it, respiratory, not enough CO2, or it's metabolic. So it's either respiratory or it's not. And if it's not, it's metabolic. If it's not, it's metabolic. All right. Some gold standards you're going to have to remember. Normal pH is 7.4. PCO2 is 40. Bicarb is 24. You must remember these numbers, particularly the CO2 and the bicarb. Particularly the CO2 and the bicarb. Yep, we got a lot of 4s in there. That magic number 4, Angela. Those are your gold standards. Got to know them. Just lock on them. X-Files. Here's my chemical reaction. That's all I'm going to work with. All right. Now, follow the bicarb. What did I mean by follow the bicarbonate trail? Here's my chemical reaction. Here's Henderson Hasselbalch. Here are my 4 basic acid-base disorders. We'll start with the respiratory acidosis. If I increase CO2, I will drive the reaction to the right, increasing hydrogen, making pH go down, and increasing bicarb. Now, question number 1 was look at theosis. pH is down. My next step, look at bicarb. So I look at pH and it's low. I look at bicarb and it's high. And I go, huh? What? I have an acidosis with too much base? An acidosis with too much base? Why, that doesn't make any sense. How can I have an acidosis with too much base? Oh, it's that CO2 thing. It's that CO2 thing. No compensation. No compensation. No, 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 no. Happens that fast. Happens that fast. It's chemistry. The CO2 goes up, drives the reaction to the right. It's straight up chemistry. We haven't even got to compensation yet. It's straight up chemistry. CO2 goes up, drives the reaction to the right. Now, if I have a metabolic, I add hydrogen, I have an acidosis, first question. Second question, look at bicarb. Bicarb's low. Acidosis, low base. Acidosis, low base. Makes sense. Makes sense, metabolic. Makes sense, metabolic. Makes sense, metabolic. If I have a respiratory alkalosis, that means I take this away. That drives the chemical reaction to the left. It drives the chemical reaction to the left. Which means bicarb goes down. So once again, question 1, I look at pH, it's elevated. I have an alkalosis. I look at bicarb and it's low. What? What? An alkalosis with low base? An alkalosis with low base? Oh, that just makes, what? No. Oh, it's that CO2 thing. It's respiratory. Just hang with it, Carolina. We're just doing chemistry. We're just doing basic chemistry. Next, if I take away hydrogen, I will drive the chemical reaction to the left. Bicarb will go down. Bicarb will go down. This is chemistry. This is chemistry. So I look at the pH, it's alkali. I look at the bicarb, it's elevated. That makes sense. I have an alkalosis with too much base. I have an alkalosis with too much base. Metabolic. If it makes sense, it's metabolic. If it doesn't make sense, it's respiratory. So again, step 1, look at pH. Step 2, look at bicarb. If it makes sense, metabolic. Doesn't make sense, respiratory. It'll work every single time. Every single time. Now, you're probably asking yourself, well, okay, if I increase CO2 and bicarb goes up, how much does it go up? How much does bicarb go up? I have a respiratory acidosis. I have elevated CO2. You just got through telling me bicarb would go up immediately. Bicarb would go up. That's what you said. Bicarb would go up. How much? How much does it go up? Well, I'll tell you. For every 1 millimeter mercury increase in CO2, you get a 0.1 milliequivalent increase in bicarb. That's how much it goes up. That fast. That fast. Chemistry. Straight up chemistry. So, pop quiz. Now notice this says increase, increase. If PCO2 is 60, what will bicarb be? This is increase in CO2, increase in bicarb. Oh, good job, Go. Good job, Go. Kanika, Teal. Y'all are all forgetting. You're forgetting your normals. This is an increase above normal. Increase above normal. That's why we have to know our normals. No, not quite. There you go. Correct answer 26. How'd you get that? PCO2 is 20 above the normal of 40. Normal CO2 is 40. Patient is 60. So it's elevated 20. 20 times 0.1 is 2. So bicarb is going to go up 2. Up from what? 24. So bicarb will be 26. Do we follow now? Do we follow now? You totally forgot your norms. You totally forgot your norms. It's up to you, Renzo, if you want to get it right or not. That's totally up to you. Does everybody see how to do it? Doesn't take very long. 20 times 0.1, 2, 24 plus 2, 26. Pretty quick. You can do it pretty quick. You can do it pretty quick. All right, CO2 was 60, so that's 20 above the normal of 40. 20 times 0.1 is 2. So bicarb is going to be up 2 from its normal of 26. 24 plus 2 equal 26 by chemistry. By chemistry. This will happen immediately. There is no compensation. It's just straight up chemistry. It's just straight up chemistry. All right. Since you were asking how much bicarb would go up with respiratory acidosis, you had to be asking how much bicarb would go down with a respiratory alkalosis, right? How much does it go down? Well, for every 1 millimeter mercury drop, I'm going to get a 0.2 drop in bicarb. Now notice, drop from what number? Drop from what number? Drop from what number in CO2? 40. Drop from what number in bicarb? Very good, 24. Pop quiz. Patient has respiratory alkalosis. PCO2 is 30. What will bicarb be? What will bicarb be? Very good, very good, very good. 22. Now you have the hang of it. Now you have the hang of it. Let's do it again. We'll walk through it real slow. PCO2 is 30. That's 10 below the normal of 40. 10 times 0.2 is 2. So bicarb is going to go down 2 from the normal of 24. Thus, bicarb will be 24 minus 2, 22. How long does it take? That long. So these are acute respiratory acidosis, acute respiratory alkalosis. You could also refer to these as uncompensated respiratory disturbances. The kidney's slow. Takes the kidney days to compensate. Takes the kidney days to compensate. So I have to distinguish acute from chronic, or uncompensated, compensated. I'm going to give you some practice questions. You'll see. I'm going to give you some practice questions. What I'm doing is showing you how to get to the answer in the practice question. You do 1, 2, 3 every single time. 1, 2, 3 every single time. 1, 2, 3. It'll lead you right to the answer. It'll lead you right to the answer. Oh, man. How can we already have time for a break? Are you kidding? There's no way. Okay. I guess we do have to take a break. It's just going too fast. It's going too fast. Time's going by too fast. We're just having too much silly fun. Dang. Okay. So that's acute changes. Acute changes. Then when we come back, we're going to talk about compensations. Compensations. Okay? We'll take 10. Yes, Darlene. The arrows go the same direction. Increase CO2, increase bicarb. Decrease CO2, decrease bicarb. Okay? Always go in the same direction. All right, let's talk about compensation. That's step number 3. Compensation, step number 3. All right, if, remember, kidneys are slow. Let's say I have a respiratory acidosis. What's the kidney going to do with bicarb? If I have an acidosis, what's the kidney going to do with bicarb? Make it go up or go down? So you're going to make bicarb go up or go down to deal with an acidosis. Yep, it's going to reabsorb it and increase it. Make new bicarb. Make new bicarb. So if I have a respiratory acidosis, the kidneys are going to kick in to compensate, but they're slow. They take days to develop, but they're going to make new bicarb. So what am I going to adjust? What am I going to adjust to distinguish? the computation for the change in bicarb. So if I have a chronic condition and the kidneys kick in, for every 1 millimeter mercury increase in CO2, I'm going to increase bicarb by 0.4 because the kidney is adding bicarbonate. Let's go back to the previous one. Pop quiz. Pop quiz. If CO2 is 60, what will bicarb be if the kidneys kick in? What will bicarb be if the kidneys kick in? What are the kidneys going to take bicarbonate to? What number are the kidneys going to take bicarbonate to? Not 26. See, now it's chronic. It's chronic. The 26 was for acute. It's 1 to 0.4 ratio. Okay? So the correct answer is 32. Excellent. Vast majority of you got that. Again, PCO2 is up 20. Is up 20. 20 times 0.4 is 8. Is 8. So bicarbonate, kidneys are going to dump bicarbonate until bicarb goes up 8 above the normal. 24 is the normal, plus 8 is 32. So if it just happened, it goes up 0.1. But over time, the kidneys are going to increase the bicarbonate pool to get it up to 32. That's going to be the compensation. So that's how I distinguish between an acute and a chronic. You're right, Surat. The book says 0.35. That is the technically correct number. But I just round it to 0.4 because it makes it easier to do the math. And it won't make a difference. So if you want to use 0.35, that is the technically correct number. That is the technically correct number. But to me, it's much easier to just calculate 0.4. And we love fours, the magical 4. Magical 4. Yep, you just need to know those basic ratios. You got it, Manel. Just basic ratios. Exactly, Sarah. Exactly. Exactly. That's why I rounded to 0.4. You'll get the right answer, I guarantee it. I guarantee it. Now, that's the kidney compensating for a respiratory problem. Let's talk about a metabolic acidosis. Respiratory system is fast. All right? Respiratory system is fast. Which means I expect a respiratory compensation to a metabolic acidosis. I expect a respiratory compensation to a metabolic acidosis. What does the respiratory system do in an acidosis? You hyperventilate. Exactly. That means CO2, I expect CO2 to go down. I expect CO2 to go down. In a metabolic acidosis, ventilation goes up, peripheral chemoreceptors, CO2 falls. 40 is no longer normal. If somebody has a metabolic acidosis, 40 is out the door. 40 is perfect, everything else when we use it, but not in a metabolic acid-based disturbance. So PCO2 is going to be less than 40. How much? We calculate it using the Winters equation. The Winters equation is 1.5 times bicarb plus 8. And the patient should be plus minus 2 of that. All right, pop quiz. I got a patient with a metabolic acidosis. Bicarb is 10. What should CO2 be? What should CO2 be? Okay, Okay? Okay? I know you transposed them, Oswald. All right, very good. 23. 23. All right, 1.5 times 10. Patience bicarb. Patience bicarb. I know you got it right. I gave you credit. I gave you credit. Patience bicarb. 1.5 times 10 is 15 plus 8, 23. Range 21 to 25. So if I have a patient with a metabolic acidosis, PCO2 must be calculated. What is now normal for this person has to be calculated. 40 is no longer normal. 40 is no longer normal. You calculate it using Winter's equation. And again, it's 1.5 times the patient's bicarb because we're diagnosing the patient. Okay? So, whoop. Darn. Okay, that header is wrong. So I found my own typo. Found my own typo. Here we go. This is compensation for a respiratory alkalosis. In an alkalosis, yeah, I get my own cookie. This is supposed to say alkalosis. Just like, we're just going to go the other direction. What's the kidney going to do in an alkalosis? Well, we went through it. It's going to dump bicarb. It's going to dump bicarb. We even went through the mechanism of it. The question becomes, how much is it going to dump the bicarb? Got a new ratio, 1 to 0.5. So for every 1 millimeter drop in CO2, you get a 0.5 drop in bicarb. Dump bicarb. Dump bicarb. How much? 1 to 0.5. Pop quiz. If CO2 is 30 and the kidneys have kicked in, so it's a chronic, what will bicarb be? Ah, you see, y'all are getting it. You're getting it. There you go. There you go. There you go. Very good. All right, 19. 19. Very good. All right, PCO2 is 10 below the normal of 40. 10 down. So 10 times 0.5 is 5. So bicarb is going to go down 5 from the normal of 24. 24 minus 5 is 19. 24 minus 9 is 5. 24 minus 5 is 19. Yeah, it's supposed to be respiratory alkalosis on the header. I'm sorry. I caught that arrow. Error. Yep, that means 19, if the kidneys have kicked in, it goes to 19. The absolute bottom limit for bicarb is 15. The absolute bottom limit for bicarb is 15 in a respiratory alkalosis. This should say alkalosis. This should say alkalosis. This should say alkalosis, not acidosis. It's not an error in your book, it's just an error on my slide. My bad. All right, now, for a metabolic, we need a respiratory response, and it's going to occur quickly. If I have a metabolic alkalosis, ventilation is going to go down, CO2 is going to go up. Ventilation is going to go down, CO2 is going to go up. That's the compensation. Guess what's no longer normal? Guess what's no longer normal? What number is no longer normal if you have a metabolic alkalosis? Exactly, 40 is no longer normal. We have to calculate it. We know that PCO2 is going to go up 0.7 for every 1 milliequivalent increase in bicarb. Go up 0.7 for every 1 milliequivalent increase in bicarb. This formula doesn't have a name, but I like to call it Summers. Because metabolic acidosis is Winters, let's make metabolic alkalosis Summers. Let's call it the Summers equation. What do you think? Help us to remember. Summers. All right? So, expected PCO2, you just take 0.7 times the rise in bicarb plus 40. Plus 40. Well, thank you, Surat, but I like Summers. I think Summers better. All right, pop quiz. I got a patient with a metabolic alkalosis. pH is high, bicarb is high. Bicarb's 34. What's PCO2 supposed to be? What's PCO2 supposed to be? Good. Very good. Now you're getting the hang of it. 47, you nailed it. We take 0.7 times 10. Bicarb is up 10. Normal's 24, bicarb is up 10 if it's 34. So 0.7 times 10 is 7. 7 plus 40 is 47. Range is 45 to 49. We'll give it 2 on either side, just like with a metabolic acidosis. Okay, some additional points. The body never ever overcompensates. Ever does it overcompensate. Don't go around to patients, you know, it looks like they overcompensated. Don't go up to them and go, high five, man, you overcompensated. Good job. You know, chest bump them and all that good stuff. You know, don't do that. Because that means they probably have 2, maybe 3 disorders. And you got them all excited when they're really in probably bad shape. You need to step back, redo it. The body does not overcompensate. If CO2 and bicarb go in opposite directions, you have a combined disturbance. Highlight this. This will save you time. CO2 and bicarb. Okay? CO2 and bicarb go in opposite direction, you got a mixed disturbance. Now, don't presume that the only time you have a mixed disturbance or a combined disturbance, these go in opposite directions. That isn't always the case. Okay? If they go in opposite directions, you know you have a mixed disturbance. But they could still go in the same direction if you have a mixed disturbance. They could. But if they go opposite, guaranteed mixed disturbance. Don't forget, too much CO2 is a respiratory acidosis. Too little CO2 is a respiratory alkalosis. Too much CO2 is a respiratory acidosis. Too little CO2 is a respiratory alkalosis. It is. It's silly fun, isn't it? And we haven't even gotten to a case yet. We haven't even analyzed blood gases yet. Now, next important thing is the anion gap. Here's the idea of the anion gap. We take the major cation, sodium. We add the 2 major anions, chloride and bicarb. And you know what? They don't add up. The difference is called the plasma anion gap. Calculated as sodium minus chloride plus bicarb. All right, what's normal sodium? Normal sodium. Excellent, 140. What's normal chloride? Excellent, 104. Beautiful. What's normal bicarb? What's normal bicarb? 24. 24 plus 104 is 128. 140 minus 128, okay, is 12. 12. You can always remember the normal range from now on. 12, you go either side. You add 2 either side, so 10 to 14. Easy to remember. Easy to remember. Now, there's not truly an anion gap here. There's some negative charges out there. We're just not measuring them. Now, this is very important in diagnosing the cause of a metabolic acidosis. When the underlying cause is an organic acid like lactate, that's more negative charge. The plasma anion gap gets bigger. If the cause of the acidosis is loss of bicarb, then the anion gap stays the same. And I got mnemonics for you. We have mnemonics. Mnemonics. What elevates the anion gap? It's a mud pile. The ones in blue are the ones I'd look for on step 1. I wouldn't worry about the P and the I for step 1, maybe step 2, but not step 1. So mud pile, methanol, uremia, that means renal failure, diabetic ketoacidosis, lactic acidosis, ethylene glycol, ethanol ketoacidosis, S or salicylate, starvation, and sepsis. So if the anion gap goes up, you have a mud pile. If the anion gap doesn't go up, you are hard up. And again, the ones in blue are the ones I would pay attention to for step 1. Previous slide is right out of your book, but remember, at the end, we'll unsync them and you can go back to them. Thank you. All right, A is acetazolamide, which is a non-specific for all carbonic anhydrase inhibitors. All right, all carbonic anhydrase inhibitors. R are the RTAs, type 1, type 2, type 4. Right? Type 1, distal. Type 2, proximal. That's a bicarb problem. Type 4, aldo. All of those have normal anion gaps. And the next is diarrhea. A non-elevated means that the anion gap is between 10 and 14. That's all it means. It's between, the anion gap is between 10 and 14. Not the same as osmolar gap. This is anion gap. This is for acid base. So, if you're doing an acid-base problem, on step 1, you define the acid base, you determine if there's compensation, and then it has an elevated anion gap. Do not put diarrhea as the answer. Diarrhea is not the correct answer. Lactic acidosis could be, sepsis could be, but diarrhea is wrong. Diarrhea is wrong. If the anion gap is normal, diarrhea could be the correct answer, and lactic acidosis is out. It's off the table. All carbonic anhydrase inhibitors. The A is acetazolamide, but that's a carbonic anhydrase inhibitor. So any carbonic anhydrase inhibitor. In other words, it doesn't specifically have to be acetazolamide. All right, mud piles and hard up. All right, let's do it again. Question number 1, what is the osis? pH is low, acidosis. pH is high, alkalosis. Question number 2, what's the cause? If I have an acidosis with too much base, I go, huh? What? You can't do, oh, it's that CO2 thing. So I know it's a respiratory acidosis. If I have an acidosis with low base, that makes sense. It's metabolic. It's a metabolic. Next, if I have an alkalosis with reduced base, I go, huh? An alkalosis with what? How can you have an alkalosis with not enough base? That makes no sense. Oh, it's that CO2 thing. It's that CO2 thing. It's respiratory. Next, alkalosis with elevated base. Alkalosis, too much base. That makes sense. It's metabolic. That makes sense. It's metabolic. So notice, after step 2, question 1, question 2, we have defined the fundamental acid-base disturbance. Now what we have to do is determine if there's compensation. Yep, you must do a calculation. Miguel, we're going to use CO2. There is, you know, the next step is going to involve CO2. We are going to look at CO2 next. Not just for fun. We look at all three. All three are always looked at. Always looked at. But we do these two first to define it. Then we're going to do something with CO2. Okay? We will look at CO2. For respiratory acidosis, I determine if it's acute or chronic. Okay? That's based upon the change in CO2. That's based upon the change in CO2. That's how I get my 1-to-1 or 1-to-4 ratio. Right? And when you look at that CO2, it's going to confirm respiratory acidosis, CO2 is going to be elevated. How much? So we're looking at all three every single time. Every single time. If I have a metabolic, I'm going to look at CO2 because I have to compare it to what it's calculated. CO2 should be low. And if it fits with what I calculate, if it's within 2, final answer, metabolic acidosis with a respiratory compensation. Metabolic acidosis with a respiratory compensation. All right, now, if it's more than 2 above, that means I have too much CO2. I have a metabolic and respiratory acidosis. Might have to put that patient on a ventilator. If CO2 is too low compared to what I calculate, if CO2 is too low compared to what I calculate, if CO2 is too low, that's a respiratory alkalosis. So I have a metabolic acidosis and respiratory alkalosis. Left off the word alkalosis right there. If CO2 is too low, then you have a metabolic acidosis and a respiratory alkalosis. How do you know if it's acute or chronic? By the level of the bicarb. If it changed at a 1-to-1 ratio, it's acute. If it changed at a 1-to-0.4, then it's chronic. All right. If I have a respiratory alkalosis, determine if it's acute or chronic. If bicarb changed at a 1:0.2 ratio, then it's acute. If it changes at a 1:0.5 ratio, then it's chronic. For a metabolic alkalosis, every time we're going to CO2, we never leave CO2 off. I have to calculate CO2 using Summers' equation. Patient CO2 should be plus or minus 2 of what's expected. If the CO2 is at the right level, then I have a metabolic alkalosis with a respiratory compensation. If CO2 is more than 2 above what's calculated, then I have too much CO2. So I have a metabolic alkalosis and a respiratory acidosis. CO2 should not go above 55. If it goes above 55, then you have a respiratory acidosis. You only have to do a calculation. That makes it nice. If CO2 is too low, then I have a metabolic and respiratory alkalosis. Not enough CO2. Not enough CO2. Remember, too much CO2, respiratory acidosis. Too little CO2, respiratory alkalosis. Yeah, it's a combined alkalosis. You got it. We're on metabolic alkalosis, not acidosis. We already defined it as a metabolic alkalosis. And if CO2 is too low, then it's a metabolic and respiratory alkalosis. All right, let's do it one more time. This is a different format. We're going to do the exact same thing one more time. Watch. This is an acid-base decision tree. Question number 1. What's the osis? If pH is low, acidosis. pH is high, alkalosis. Next step, let's start on the acidosis side. What is the cause of the osis? You look at bicarb. If bicarb is elevated, you go, what? You go, what? An acidosis with too much base? What? Oh, it's that respiratory thing. Step 3, compensation. Determine, is it acute or chronic? And that's based upon the bicarbonate change, 1:1, 1:0.4. So notice, 1, 2, 3. Let this tree guide you to exactly what you're going to do. 1, 2, 3. It takes you exactly to what you need to do. If you look at bicarb and you have an acidosis, that makes sense. If bicarb is low and an acidosis, that makes sense. Use Winters to determine if they had a respiratory compensation. You must determine what CO2 should be. Yep, this is where the money is. All right, if I have an alkalosis, I look at the cause. To determine the cause, I look at bicarb. If bicarb is low, I go, huh? Alkalosis with not enough, huh? Oh, respiratory. It's that respiratory thing. Determine if acute or chronic, 1:0.2, 1:0.5. If I have an alkalosis and the bicarb is elevated, I say that makes good sense. It's metabolic. Now I must calculate what CO2 should be. This will guide you right to what you need to do. This is just a summary of everything we just talked about. Note, PCO2 goes up in a respiratory acidosis, compensatory increase in metabolic alkalosis. CO2 goes down in a respiratory alkalosis, compensatory decrease in a metabolic acidosis. Calculate the anion gap. Calculate the anion gap. Calculate the anion gap. That's where it fits right. Calculated. Calculated. All right, let's practice. Don't look at your book.